Hey everybody, lesson 7.1. Today, let's consider this triangle up in the upper left-hand corner of this screen here. It's got a 35-degree angle in it. You've learned by now that if I asked you what is the measure of angle TIR, that the appropriate response would be cannot be determined, or we don't know, something to that effect. It's true that angle TIR appears to be congruent to angle TRI, but we rarely make judgments in this class based on appearances. However, if I told you that triangle TRI was isosceles with base RI, now I'm giving you more information about that triangle. And if you know the definition of an isosceles triangle, you understand that part of the definition is that an isosceles triangle has two congruent sides, two congruent base angles, and then you could tell me with conviction, with certainty, that angle TIR is also 35 degrees. Well, we're into the same kind of territory here, but today with all kinds of quadrilaterals instead of triangles. Quadrilateral literally means four sides. So all kinds of four-sided figures we're talking about today. And you're familiar with most, if not all, of these particular kinds of four-sided figures. I've got two figures here. This one is a square, and this one right here might go by a variety of names. Some people might call it a diamond. Technically, in geometry, it is called a rhombus. Okay, and now I'm not going to be asking you to know the definitions, the formal technical definitions of all these different types of four-sided figures that we're going to be talking about today. What we are going to want you to know is a lot of the properties, a lot of the characteristics of these specially named figures. And while I'm talking about all of these specially named figures, all having four sides, let's just take a quick look at what they are. Here's the homework assignment for tonight, but on the first page, here's all of these special kinds of quadrilaterals that we're going to be talking about. Here's a square down at the bottom. You're very familiar with squares. They have four congruent sides, and they have four right angles in them. A rectangle has also four right angles in it. It has two sides that are congruent to each other. The other two sides are also congruent to each other. Okay. Here's the figure we were just looking at. You might call it a diamond because that's kind of what it looks like, right? But the technical word is rhombus. And a rhombus, by definition, has four congruent sides. Look at all four of the sides of that rhombus. Don't they all seem to be congruent to each other? Now, that's also true that a square has four congruent sides. And so technically, a square is a kind of a rhombus, because all you need to call a quadrilateral a rhombus is to know that it has four congruent sides. Now, if it has more stuff that's true about it than that, it's still a rhombus. Okay. Like the square has four right angles in it, that doesn't make it not a rhombus. A rhombus is not a rhombus because it has four congruent sides and it's got these certain angle sizes, or it looks like a diamond or anything like that. It's just four congruent sides that makes a quadrilateral a rhombus. So a square is actually technically kind of a rhombus. For that matter, a square is a special kind of a rectangle too. We could call this thing right here a rectangle and you wouldn't be wrong. Okay. And again, I'm not going to trouble you with these technical definitions at any point this semester, but it is something that we would trouble you with a good deal if we were in the building. And I just want to mention it in passing. I think it's important to at least mention that when you're a little kid and you're playing with blocks or shapes, okay, and somebody says to you, now let's say you've got a block in the shape of a rectangle and a block in the shape of a square, and somebody says to you, where's the square? Can you find the square? Pick up the square. And you pick up the square and they go, yay, the square, right? And then they say to you, pick up the rectangle. And what if you pick up the square again? Probably somebody at some point in your young life said, no, that's not the rectangle. But they were wrong. Okay? They were wrong. A square is a special kind of a rectangle, but you probably were taught wrong as a younger person, or maybe somebody didn't specifically teach you wrong, but they didn't really teach you right, that a square is actually a type of a rectangle. It's a rectangle that's more, well, squarish, okay? But it is a kind of a rectangle. And rectangles and squares and rhombuses are all special kinds of parallelograms. And maybe you were never taught that, but you've probably heard the word parallelogram. And technically, what that means is any quadrilateral that has two pairs of parallel sides. So these two sides are parallel, and these two sides are parallel. As long as you have two pairs of parallel sides, you can call the figure a parallelogram. Well, all of these other figures here have two pairs of parallel sides. So they are parallelograms, but this one's more rectangularly. So we call it a rectangle. This one's more rhombusy. It is a parallelogram, but it's more rhombusy than your average parallelogram. Okay, so we could call it a parallelogram, but saying that it's a rhombus gives us more detail, tells us more information about the figure, right? And calling this a parallelogram, well, it's true, but calling it a square tells us more detail about it, right? And then there's these figures over here. Again, you were probably taught incorrectly. Anytime anyone ever said trapezoid, you probably were shown or pictured something like this, which technically is an isosceles trapezoid, because this figure right here, this qualifies to be a trapezoid. Technically, the definition of trapezoid is that you've got one pair of parallel sides, and the other two sides do not have to be parallel. Well, that's true about this figure right here. It's got one pair of parallel sides. That makes it a trapezoid. Okay. Now, besides the parallel sides, like in this figure down here, if the other two non-parallel sides are congruent to each other, then you've got an isosceles trapezoid, much like an isosceles triangle has two congruent sides. An isosceles trapezoid has two congruent sides. And just like an isosceles triangle has two congruent base angles, this isosceles trapezoid also has two congruent angles at the bottom, and it's got two congruent angles up at the top as well. Okay. And then there's this thing called a kite, which is a great name because that's kind of what it looks like, doesn't it? It looks like the kind of kite you'd go out and fly. And technically, definition of a kite is it's got one pair of congruent sides up here and another pair of congruent sides down there that have to be different from those. Again, we're not going to bother you with the technical definitions. What is the definition of this? What is the definition of that? We're not going to ask you questions like, hey, could you call this rectangle a square? Could you call it a parallelogram? These are the kinds of questions that we would delve into if we were together in the building and had a lot more time, but it's one of the things that we've chosen to kind of skip over. But the properties of these things, no. So let's get back to a lesson about stuff that you got to know today. Again, this thing here is a rhombus. I've created it so that no matter how I stretch it or shrink it, all four sides of this quadrilateral always stay all congruent to each other, right? And I could spin this thing around. It doesn't matter which way it's facing. It's still a rhombus. All four sides are congruent to each other, okay? Speaking of, it doesn't matter which way it's facing. This thing over here, which is a square, I built it to be a square. It doesn't matter if you turn it around this way. It's still a square, okay? Now, it looks more like a diamond, and so it looks more like a rhombus, but the fact is, any square technically is a rhombus. But my point here right now is that it doesn't matter which way anything is facing. We are almost never concerned in geometry about which direction something is pointing or facing. That makes no difference to us at all. And so this thing is still a square as long as all four sides are congruent and all four angles are right angles. Okay. But back to what I started with at the very beginning of this lesson. This triangle, if I don't tell you that there's anything special about this triangle, you can't tell me that angle TIR is 35 degrees, even though it looks like it's the same as angle TRI. But if I tell you it's an isosceles triangle with base RI, now we know that there's more stuff that's true. There's more specialness about that triangle, and there are congruent things in various places. And that same idea is true about all of these special kinds of quadrilaterals here. If I tell you that something is a parallelogram, I don't just give you a quadrilateral and say nothing about it. But if I tell you it's a parallelogram, or if I tell you this quadrilateral is a rhombus, or any of these special named quadrilaterals, then there are lots of congruent things in a variety of places in those figures. And it can be we can prove this going back to my rhombus, for instance. This rhombus always has four congruent sides in it. So here's what's true about the rhombus. I'm going to make some marks in it. I can get my stylus to work. Okay. It's got four congruent sides. Technically, that is the definition of a rhombus. Okay, as long as we know a quadrilateral has four congruent sides, we can call it a rhombus. It satisfies the definition. It meets the definition of rhombus. Okay, but look at this triangle, and I'm going to name some letters now. Let's call this, not triangle, rhombus. Look at this figure, A, B, C, D. Let's call this point right here at the center. Let's call that point M. I've got triangle DAB. Clearly, that's an isosceles triangle, right? Triangle DAB, that big triangle on the top, because it's got two congruent sides. And if it's an isosceles triangle with two congruent sides, then it has also two congruent angles, right? And triangle DCB, the one on the bottom, triangle DCB, that's also an isosceles triangle. And so it also has two congruent angles. This one is congruent to that one. Okay. But here's what else is true. This side here, segment DB, is shared by triangle DAB and triangle DCB, right? So if I put a double slash on that side, now I've got triangle DAB, the one on the top, congruent to triangle DCB by SSS. And therefore, corresponding parts of those two triangles are congruent. And therefore, this angle from triangle DAB is congruent to this angle from triangle DCB. And so now I don't have to use different kinds of congruent marks for those two pairs of angles. I actually have all four of these angles. 1, 2, 3, 4. They're all four congruent to each other. And don't they look all four congruent to each other, right? But looking congruent to each other is not the reason that we know they are congruent to each other. I just proved to you that they would have to be congruent to each other by getting some congruent triangles in the picture, right? We could do the same exact reasoning to prove that this angle, this angle, and this angle are all congruent to each other, all four of those angles. And they certainly look congruent to each other again, don't they? Don't they all four look like they're about, I don't know, 60 degrees, right? But again, looking like it is not the reason. Okay. It's fairly easily proved. Okay. And then there are other congruent things in this picture. And let me erase the marks there so they're not so distracting. Okay. But there are other congruent things in this picture. And again, we're starting off with the knowledge that the four sides are congruent. That's what makes it a rhombus in the first place. Okay. But here, this segment, doesn't that look congruent to that one? It could be proved that those segments are congruent by getting some congruent triangles in the picture. That wouldn't be hard at all. It could be proved that segment MB is congruent to segment MD. Okay. And it could be proved fairly easily that all of these angles at this intersection, don't they all look like right angles? Well, that could be proved also. Wouldn't be hard at all. Okay. Now, we're done technically in this course, this semester, with asking you to prove things. But I want to really make the point here that all of these things that are congruent could be proved, and you have the knowledge and the ability to prove all of these congruent things. Okay? But in the homework tonight, I'm going to be asking you for measures of things without asking you to go through a formal proof, right? And here's the kind of thing I'm talking about. So now we're getting into some examples right now. A few examples, and that's the end of this lesson. Suppose I give you, again, that this quadrilateral figure, RHOM, is a rhombus. Okay? My telling you that allows you to conclude that there are lots of congruent things in a variety of places in this diagram, okay, without having to prove them. If I didn't tell you this was a rhombus, you'd be stuck. You wouldn't be able to conclude anything with certainty. But when I tell you it's a rhombus, then we can conclude lots of things. So let's get after it. All right. I've given the measures of certain things. I'm asking for the measures of lots of other things. First one here, segment VO. Here's segment VO. Well, because this figure is a rhombus, segment VO is going to be congruent to some other segment in this picture. Guess which? Yeah, segment RV, which is 5 centimeters long. So VO is also going to be 5 centimeters long. On the basis of this picture, if I had asked you the length of RO, you'd be able to tell me, well, let's see, RV is 5, VO's got to be 5, RO would have to be 10. MH, okay, MH. Well, that segment actually doesn't appear to be congruent to any other segment in this picture. It appears to be actually longer than any other segment in this picture. But look, MV is given to you to be 12 centimeters. So then VH would also have to be 12 centimeters. And therefore, MH is going to be 24 centimeters. Okay. How about the perimeter of this figure? I think you know the meaning of this word, perimeter. It means the measure around, the length around, the total length. Add up the length of all of these sides going around. Not the lengths of any sides cutting through the middle, none of the diagonals or anything like that, just the lengths of the sides going around. By the way, this prefix in the word perimeter, peri, you are familiar with that prefix in other words, or a word at least. I'm sure you've all heard of the word periscope, right? Where do you find periscopes? On submarines, right? And in a periscope, somebody's looking in this thing, and what can they do with a periscope? They can spin this thing around and look completely around in 360 degrees. That's the peri part of that word. The scope is the looking part of the word. You can look around 360 degrees with a periscope. Okay. So a perimeter is the distance around. And what is the distance around? Well, if this side of the rhombus is 13, that's got to be 13, that's got to be 13, and that's got to be 13. So add up all of those 13s or use some multiplication. Okay. 13 times 4 is 52 centimeters. And there's your answer there. How about these angle measures? MVR. Let me erase some of that stuff that I've drawn up there so it's not so distracting anymore. Angle MVR. Where is it? Where's angle MVR? Oh, well, it's right here. Doesn't that angle look like a right angle? Okay. Now, I know 100 times this semester, I've told you, do not assume that just because an angle looks like a right angle, that it is a right angle. But we wouldn't have to assume this is a right angle. We could prove this is a right angle. We really could. If we know all four sides are congruent, it would be very easy to prove that this triangle is congruent to this triangle, and therefore that this angle is congruent to this angle. And if you've got two angles side by side that are congruent to each other and they're forming a straight line, which is 180 degrees worth of angle, right? And you split that 180 degrees into two congruent parts, they've got to each be 90. It would be so easy to do that. Okay? But all I'm asking you to do in this unit is to say, well, it's a rhombus, so this is a special kind of quadrilateral. It's not some random quadrilateral. And if things look like right angles, they're right angles. Okay, so MVR would be 90 degrees. Okay, how about angle VRH? Again, let me erase what's in there. But MVR, 90 degrees. Put that in there. VRH is up here. Well, that angle does not appear to be congruent to this 25 degree angle. It certainly does not seem to be a right angle either. How are we going to find that angle measure up there? It is findable. Okay. Well, wouldn't this also be a 90 degree angle right there? Doesn't it look like a 90 degree angle? And now, don't we have 2 out of 3 angle measures in this triangle? We've got a 90 degree angle. We've got a 25 degree angle. Add those together, you get 115. Subtract those from 180, and you get 65 degrees for that angle up there. Come on, let's get rid of those. 65 degrees. So that's 65 degrees. And then angle RMO. Okay, RMO, this one here. Well, I've got this angle is 25 degrees. Okay. Aren't there other angles in this picture that appear to be 25 degrees? That one's 25, that one's 25, that one's 25. All 4 of those angles are 25. If this is 25 and this is 25, that makes angle RMO 50 degrees. Okay? You're going to have to use everything you've learned about, well, maybe not everything, but a lot of what you've already learned this semester about angle measures and how to find angle measures and apply it to these diagrams here. Okay, but you should rely on visual judgment. Okay, but the only reason you're allowed to rely on your visual judgment is because I'm going to draw good pictures of these special kinds of figures, and I'm going to tell you that they are these special kinds of figures. Let's look at another example. Okay, if I tell you that this figure is a rectangle, now you're allowed to use your visual judgment to decide, well, again, there's lots of congruent parts over here. So let's look for segment RT's length. RT. How long would that be? Well, wouldn't it be the same length as this segment over here, 10 centimeters? Sure it would. And again, I feel compelled to say this over and over again in this lesson. We're not really coming to that conclusion just because they look the same, but rather because they look the same and we've been told that this is a rectangle. Okay. RC, how about the length of segment RC? That whole segment there. Think about that for a second. Any ideas? Well, this is 13, so that's also 13, and that's also 13, and that's also 13. Don't all four of those segments appear to be congruent to each other? So the length from R to C is 13 plus another 13, 26. There's a lot about this lesson where I can't give you a step 1, step 2, step 3 way to solve a problem. You've got to see things. You've got to be looking for and seeing things that appear to be congruent in the picture. And I can't give you like a step 1, step 2 way to find these things. You got to look. Okay. The perimeter of RECT, well, again, the distance completely around the rectangle. None of the segments on the inside, just the ones going around. 10 plus 24 plus that would be another 10, right? And then that would be another 24. So 10 plus 24, and then either add another 10 and a 24 or just multiply that whole thing by 2, and we would get 68 centimeters. How about the measure of RME, angle RME? Let's get rid of all of those messy lines. Okay, where's angle RME? RME, right there. Certainly does not appear to be a right angle, does it? Does it appear to be acute or obtuse? Obtuse for sure. And hey, look, it's right next to a 50-degree angle. There's a linear pair right there, right? You remember that phrase, linear pair of angles right next to each other, forming a straight line, which is 180 degrees. So subtract this 50 from 180 and you'll get 130 there. I said earlier, you're going to have to use a lot of what you've already learned this semester about finding angle measures. The fact that this angle is 130 really has nothing to do with the fact that this quadrilateral is a rectangle. I wouldn't have to tell you that, right? I wouldn't have to tell you anything about this quadrilateral at all for you to be able to tell me that this angle is 130 degrees. That's based on something we learned months ago. Okay, so that's 130. How about angle MTC? Where's that? Again, I want to erase some of the other stuff going on in here. MTC, where's that? Angle MTC, right here. Okay. Well, again, every angle measure in this quadrilateral is related in some way to some other angle or angles in this quadrilateral. Does that angle appear to be congruent to any other angles in this quadrilateral? Sure, it appears to be congruent to that one. And doesn't it also appear to be congruent to that one and that one? So angle MTC is 25 degrees. And how about angle RCE? RCE. Let me get a different color for that one. RCE. Well, that certainly does not appear to be congruent to the 25-degree angle that it is right next to. So I'm not going to say 25 degrees. Any ideas about how to come up with that blue angle? Well, there's more than one way to come up with it. Here's one way. If this is 50 degrees here, then that's got to be 50 degrees there. And doesn't this triangle here appear to be an isosceles triangle with congruent angles there? Yes, it is. So if we subtract this 50 from 180, we'll get 130. And then if we split that in half, we'll get 65 for each of those angles. This one here and that one up there. Or here's another way to do it. since this quadrilateral is a rectangle, okay, and I just erased one of the numbers in this, 25 degrees. Since it's a rectangle, isn't this a right angle there? Isn't it 90 degrees? So 90 minus that 25 is equal to 65. That would be another way to get that angle there. I don't care how you get it, just get it. Okay, so angle RCE is 65 degrees. Let's move down. A couple more examples here. Recall, as I've written here from earlier in the semester, that when two parallel lines are crossed by a transversal, that word transversal literally means something that's crossing two other things, okay? When two parallel lines are crossed by a transversal, that any two of the angles formed by the intersections are either congruent or supplementary. Remember when we were doing this? I marked parallel lines here. We got 8 angles. 1, 2, 3, 4, 5, 6, 7, 8. You pick any two out of those 8, and those two have to be either congruent or supplementary, meaning they add up to 180 degrees. Okay? Well, most of these special figures are parallelograms, meaning they have two pairs of parallel sides. And a parallelogram, that's literally the definition, that you've got two pairs of parallel sides. But rhombuses, rectangles, squares, they're all types of parallelograms with parallel sides running across in both directions. Now, a trapezoid or an isosceles trapezoid's got one pair of parallel sides only, okay? And a kite actually has none. But these other 4, they all have lots of parallel sides. So, okay, if I'm looking for the measure of angle LPA, which is up here, what you have to recall is that we've got in a parallelogram 2 parallel sides here. And then here's a transversal, creating this 50-degree angle and this fairly obtuse looking angle, which would obviously not be 50 degrees, the same as this one down in the lower left-hand corner, but if they're not congruent, then they must be supplementary. And so we would subtract 50 from that 180, from 180 to get 130 degrees. These two angles here, if they're not congruent, they've got to be supplementary. Okay, so angle LPA would be 130 degrees. Let's add that to the picture. Okay, 130. How about angle LRA? LRA, that angle right there. Well, we could do the same sort of analysis to find the measure of that angle as we did to find the measure of angle LPA up there. We've got 2 parallel lines here because this is a parallelogram. 2 parallel lines. And then in red, here's a transversal crossing both of those blue lines or connecting both of those blue lines. This 50 and this obtuse angle, clearly not congruent. It must be supplementary. Subtract the 50 from 180. This has got to be 130. But you know, here's an even easier way, as far as I'm concerned, to decide that this angle LRA must be 130 degrees. Doesn't it appear to be the same size as that angle up there? I mean, once we know this angle measure in the parallelogram, then this angle measure has got to be the same. Okay, so 130 degrees for that. And angle PAR, which is up here, doesn't that appear to be congruent to this one? 50 degrees there. Or again, we could use the parallel line analysis or the parallel line approach to finding out that this is also 50 degrees. Okay. Now, what about X? I'm asking for the value of X here. How are you going to find that? Here's what you won't do. You won't set 8x minus 30 equal to 180. Wrong, wrong, wrong. That's one of the more common mistakes I see the students doing. And I kind of think I know why they do that. They see this 8x minus 30 written alongside a line. I've asked lots of questions about angles here. Their brain is in angle mode. They think, oh, straight line 180 degrees. And they set that 8x minus 30 equals to 180. But look, what's next to the 8x minus 30? What is that an abbreviation for? Centimeters. That's a length. I'm telling you that the length of this segment, that's how you have to understand how to interpret this diagram. The length of that segment is 8x minus 30. And a segment length does not have to be 180, right? A segment length could be anything at all. It could be 20, 50, 8.6, right? It could be anything. I don't know what that 8x minus 30 equals. And neither do I know what this 3x plus 12 equals. But couldn't we say something about this 8x minus 30 and this 3x plus 12? Don't they seem like they should be related to each other? They're opposite sides of this parallelogram. Don't those two sides look like they are congruent to each other? Same with these two sides. Don't those two sides look like they are the same length as each other? So the correct equation to set up here would be that this 8x minus 30 equals this 3x plus 12. And then do a little bit of algebra to solve the equation. Subtract 3x from both sides, add 30 to both sides. 5x is 42. Divide both sides by 5. You're going to get x turns out to be 8.4. Nothing wrong with a decimal answer. Okay, that's how we would get the value of x, by recognizing these two lengths are equal to each other. It's not that either one of them is equal to a specific value, okay, but rather that they're equal to each other. And I got one more example, okay, down here. I'm telling you, this is an isosceles trapezoid, all right? So we got parallel lines here. I don't have to mark them. If I tell you this is an isosceles trapezoid, okay, that by definition, that means these lines are parallel. By definition, it means these segments are congruent. And then there's all these other congruent things going on that, again, we could prove, okay? But I'm asking you to determine on the basis of things looking congruent to each other. Provable, but we're not asking you to prove them, okay? So let's start again with x here. X. Ooh, well, that 2x plus 8, we're going to have to put that into an equation. It's got to be equal to something. Okay. You suppose it's equal to 120 degrees? No, come on, look at this angle. Does that look like an obtuse angle? Does that look like 120 degrees? No, definitely not. Okay. It looks like it might be equal to this angle over here, but I haven't given a measure of that one either. So I'm not sure how helpful that is. Right. So what do we do? Well, again, this is an isosceles trapezoid. Two of its sides must be parallel. And if we have two parallel sides, and those parallel sides are being crossed or connected by a transversal, then any two angles formed by those parallel sides and the transversal must either be congruent to each other or supplementary to each other. Clearly, these two are not congruent, so they must be supplementary. And so you could, I suppose, write this equation, 120 plus 2x plus 8. That's all got to add up to 180. My guess is most of you would do a little bit of arithmetic in your heads, and you would say, oh, if these two angles have to add up to 180, and that one's 120, subtract that 120 from the 180, and you get 60 degrees left over for this angle down here, and you might start right away with this equation, right? Which is what you would get, of course, if you subtracted 120 from both sides of this equation. But a lot of you would probably start right off with this one, which would be fine with me. Subtract your 8 from both sides, divide both sides by 2. X turns out to be 26. There you go. Okay. How about the measure of angle ITO? That's this one here. Well, that's going to be congruent to that angle over there, 60 degrees. And this angle up here, angle TIS, obtuse, going to be congruent to that one there, 120 degrees. Okay. Most of your homework problems tonight will not involve setting up equations, but some of them will. Anytime I've got, an X or a Y or a Z, some algebraic expression in some angle or segment in a diagram, you're going to have to set up an equation. And the equation might be setting an expression equal to, not some random number, but some number that you have determined from other work in the diagram. You might be adding things up to get 180. You might be setting things equal to 90. That's a common occurrence in these types of diagrams. Let's go take a quick look at the homework itself. Here's the homework. The front page is not homework. It's just a reminder of what's key in this lesson here, which is that if you know that a quadrilateral is special in some way, meaning it's one of these special kinds of quadrilaterals, then a well-drawn picture of the quadrilateral gives you the opportunity to use your visual judgment. And I emphasize well-drawn. I mean, if let's go back to this page over here. If I draw a picture like this, and I say, well, let's draw a picture like this, and I say, well, that's a square. Okay. And tell me the measure of that angle there. Well, I don't know that you could tell me the measure of that angle, but this thing does not look like a square, right? If it's a well-drawn square, like this one here, and we put these diagonals in, and then I would expect you to know that that angle there, where the two diagonals are intersecting each other, that's a right angle, because it looks like a right angle, okay? And I'm never going to draw pictures of these quadrilaterals that don't look like what they are truly supposed to be, okay? So if segments look congruent, they are. If angles look congruent, they are. If angles appear to be right angles, they are. These are things that we were never allowed to assume before today. And even today, we're still not assuming them, okay, because they are provable when we know that these figures are special, all right? So here's a sneak preview of the homework. I'm asking you for segment lengths, angle measures. Sometimes I'll ask you for a perimeter, like down here. Anything unusual going on in any of these problems? I'm just taking a quick look. Oh, page 3, all of these problems not involving quadrilaterals, just giving you some practice on finding angle measures based on stuff we learned a while back, because we've got a major test coming up. We've got one more lesson about angles after this one more lesson, and then we will have a major test on finding angle measures, okay? And it's going to include all of this stuff that you learned a while ago this semester, plus the new stuff we're just learning today on quadrilaterals, plus the new stuff we're going to learn in the next lesson, okay? So it would be good to start doing some practice on all of that old stuff now. So that's part of the homework today, all right? Get going.